Poisson random variables, again, they come up in nature because of this sort of limiting of the binomial, but it is easy to get mixed up on what they are and what they aren't. Again, the binomial, I think, is very straightforward. It's like counting the number of coin flips. But what is the Poisson? I guess we're going to find out in a second when we do these tricky true-falses. So is it possible that the random variable will not be a whole number? Like, could it be something 0.7? Could it come up to something 0.7? And people said, drumroll, 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 ooh, 16 to 29. 16 people said true, it's sometimes a decimal number, and 29 people said false. It is always a whole number. And in this case, the majority has it right. It is always a whole number. So remember, the Poisson is counting the number of things that happened, like the number of whales you saw. You can't see half a whale. How many times you saw a whale? It's the same thing with binomial, right? It's either a success or a failure. That's the two options in the binomial. And the Poisson is the same thing. X is a counting variable. It's counting the number of things that can happen. All right, what about, if you didn't peek ahead, what about the parameter lambda? What about the parameter lambda? Because in the binomial, we had this parameter n, and n was always a whole number. But now we have this weird parameter lambda, it's a crazy-looking Greek letter. And in this situation, 38 people said true, it's sometimes a decimal number, and that is absolutely correct as well. So very good. If you got true for this one, you were paying attention last class. And the reason is lambda is the average number of things you see. And of course, even if you always have a whole number, the average doesn't have to be a whole number. If half the time you see one whale and half the time you see two whales, then the average will be 1.5. So that makes perfect sense. It's the average lambda can be a decimal number, even though the actual realizations are always a whole number. And last class, we did an example where we saw 1.2 whales per day on average. Very nice. OK. Righty. Let's pretend that you didn't see the last answer. Hoo-hoo. In this one, I said to calculate the probability x greater than or equal to 2, that's the probability you see at least 2 whales, one must do an infinite sum. And out of 45 people, we're pretty split here. So true, some people said it's an infinite sum, but 27 people said false, you can do it as a finite sum. And what is the correct answer? It is both. Both. Why is it both? Well, it is an infinite sum, but you can do it as a finite sum. And so this is one of the nice tricks in probability. We've already seen this before with the geometric random variable. Even though you would technically have to do an infinite sum, there is this nice 1 minus trick of doing the complement that we've done since the beginning of the year that lets you do it as a finite sum. So let's do that now and make sure. Yes, any questions or comments from the peanut gallery?
Well, I do have a question from the peanut gallery. Let's look back at your question.
Oh, let's look at my question. OK. Yes.
Now, the question is, it says one must do an infinite sum rather than one can do an infinite sum.
One must do.
One must do an infinite sum.
One must do. Yes, I know.
So
okay.
I will argue it can be done.
So this is the problem. This is not
sum.
a math. This is a statement about humans, right? And you can't make any true-false statement about humans.
Well, no, I will argue that one is.
All right. Well, the way I worded the options, I think it's both. You're right. If I only said true or false, I guess it would be false. No, look, any infinite sum, right? Maybe there's some tricky way to do it. So there's like the real answer would be we don't know. Anyway, okay, it doesn't matter. We're getting in the weeds. Let's do it both ways. Let's do it both ways, and let's see it both ways. By the way, for those of you who are interested in Guess Who, I posted a recording of the lecture I gave last week on Guess Who. You can go check that out if you missed it. But let's work on Poisson random variable. So let's do the number of whales, and we said the number of whales. Let's call that x, and x was a Poisson with parameter 1.2, and we are interested in the probability x is greater than or equal to 2. And very technically speaking, the probability x is greater than or equal to 2 is an infinite sum. It's the sum from 2 to infinity of the probability that x equals lowercase x. So it's 2 or 3 or 4 or 5 or 6, all the way up to infinity. Big infinite sum. And this is an absolutely true statement. The probability is an infinite sum, just like the geometric random variable. And you could write down the formula for this. It would be e to the minus lambda, which in this case is 1.2. And then you would do lambda to the power x, 1.2 to the power x, divided by x factorial. So summing up this big infinite sum. Unfortunately, this sum's quite annoying and hard to do. But there is a trick, as always, which is you can write it as 100%, let's write it like this, 100% minus the probability the opposite of x is greater than or equal to 2. Let's do x is greater than or equal to 2, complement. Complement the opposite of x is greater than 2. And this is something you can always do, going all the way back to our first week of class. And in this situation, if x is not greater than or equal to 2, then x is less than 2, also known as, let's say, less than or equal to 1. Let's do it that way, because it's always an integer. So yeah, this is always something you can do with random variables. And in this case, this is some nice thing, 100% minus. And the probability x is less than 1, it's either got to be 0 or it's got to be equal to 1 exactly. Okay, that's very nice. Okay, and now we can do this.
One more comment from the peanut gallery.
Yes, please.
Your use of 100% in place of 1.
Oh,
We have to recognize that.
you don't like that.
Nah.
Percent. This little symbol to me just means 1 over 100. So this is 100, 1 over 100.
As long as we recognize that is.
What else could it mean? Yes, this is true. Okay, this is very technically. You could put 1. Look, the reason I did 100%, I didn't want to mix up this one with this one, right? This one is a probability, 100%. This one is a counting, how many whales you saw. And they're both 1, because of course 1 is an important number that comes up everywhere.
But we would not want anybody to subtract those probabilities from 100.
Yeah, that's true. If you forget the percentage sign, it's totally wrong. Yes, very good. Yeah. Okay. Yeah. Let's not be cavalier about this 100%. Actually, recently I was working on a student's project and they mixed up dollars and cents. They said there's something that was 18 cents and they said it was $18. Of course, it's still the number 18, but you can go bankrupt pretty quick if you mix up dollars and cents. There's a famous Verizon thing where they have 0.02 cents per kilobyte versus 0.02 dollars per kilobyte on your cell phone plan, and there's quite a big difference. There's a very funny video of them trying to convince the customer support people. Maybe this is before your time. This was when I was peak on the internet. Okay, anyway, yes, so units are important, and in this case, the percentage sign, very important. Okay, let's finish off the answer, and if you want, I can switch back to 1, because 100% equals 1. 100% equals 1, and the probability is equal to 0. That is nice, e to the minus 1.2 times 1.2 to the power of 0 divided by 0 factorial minus e to the minus 1.2, 1.2 to the power of 1 divided by 1 factorial. And 0 factorial is 0, and anything to the power of 0 is also 0. So 0 factorial is 1. Oh my goodness, what am I saying? 0 factorial equals 1, and 1.2 to the power of 0 is also 1. 0 factorial is 1 because there's only one way to arrange no things. Look, here are my no things. Here I've put them in order for you. That's the one way. Okay. Let's not get into a debate. Okay. E to the minus 1.2 minus e to the minus 1.2 times 1.2. Okay. And then you type it in your calculator, and you get some answer.
A simplification, though. Very common in these questions.
Ooh. What's
to factor out the e
you factor
to the
this
negative
out? Okay.
1.2, e to the negative lambda.
Save yourself a little bit of work on your calculator. 1 plus 1.2. Yeah, that seems right. Okay. Okay, you put it in your calculator and you get a number. Let's not speculate what it is. Let's just say I put it in your calculator and get a number. Okay, any questions or comments about this one? I will say if you're paying attention to this whole thing, you might realize something, is that we have actually made a statement about a really crazy infinite sum. And we have claimed that if you do the sum starting at 0, from x equals 0 to infinity, and you do e to the minus 1.2 times 1.2 to the power x divided by x factorial, that must be exactly 1. And that's the sum over all of the different things it could be. And of course, it's got to be something, so that's 100%. But this, if you just multiply both sides by e to the 1.2, you get this identity. 1.2 to the power x divided by x factorial is e to the plus 1.2, because it comes across with a sign like this. And this is a true statement about the exponential function that you might have seen in calculus class. So another way to write this is true for any lambda. Lambda to the x over x factorial equals e to the plus lambda. And this thing is the famous series 1 plus lambda squared over 2 plus lambda cubed over 3 factorial plus dot, dot, dot. This infinite sum adds up to e to the lambda. If you've been taking a good calculus class, you'll encounter this at some point, and it's got something to do with the derivatives of E, and it's a Taylor series expansion of stuff, all sorts of beautiful things. This is how I personally, this one is baked into my memory from my calculus class, and this is how I remember the Poisson distribution. It's you take the Taylor series for e to the lambda, and those are the probabilities. Probably I'm the only person in the world who does this, but okay. All right, I think that's all I wanted to say about the Poisson and doing our problem about the number of whales. Questions or comments? All right, let's learn about some other applications of the Poisson over here that Professor Humphrey will show us.
What did that come out to?
Hold on. Yes.
What did that answer come out to?
Oh, I don't know. Did anybody do it? Anybody put that in the calculator? Oh, we have to get our calculator out. Okay, let's do our. Fortunately, I have a little calculator in my pocket over here, and my calculator is called Google. Okay, e to the minus e little caret sign minus 1.2, and then put in brackets. Make sure you do the brackets right. Times 1 plus. Oh my goodness gracious! Where's the plus sign? Plus 1.2, search, Google says 33%, 0.3373 equals 33.73 ... percent. That's what I got. 1 minus, yeah. Okay. Does that seem about right?
That is good. That is good.
Okay.
And I think if you work out the probability of exactly one whale, it comes out to 30-some% too. And of course, that's just the single value that was worked out for the probability x equals 1. Yes. So what did I have to say? What did I have to say? Well, an interjection in here. Okay. I am kind of amused. Well, not amused isn't the right word. I find it curious as some of the odd ways that strange accidents can happen. This was one in the New York Times a few years ago. Though not common, 136 injuries similar to this toothpick case study have been reported in medical journals, and nearly 10% were fatal. And you're looking at this tasty food, and maybe you've encountered this before yourself when you've been eating. But what is the accident? Swallowing a toothpick. Now, if you actually go to this article, I'm not sure you can because I think you need access to the New York Times to get there. I have access, but maybe you can't see it. Anyhow, it discusses how ghastly the guy was actually a school athlete, swallowed this toothpick, and then it gets into your intestine and punctures things, and then it gets infested. Multiple surgeries, horrid stuff, and as you can see, about 10% of the time, it was fatal.
Well, no, wait, hold on. The ones reported to the medical journals, 10% were fatal, probably in real life.
And probably in real life.
Probably lots of people eat the toothpicks, and then nothing happens, and then nobody hears about it. It's just someone died, and it's all in the medical journal.
Exactly.
So, yeah.
So there was a few years ago, and I can't remember what year it was, I saw a bit of news that 3 people in the United States had died one year from swallowing bay leaves. How many have had food cooked with bay leaves in it? Okay, lots of people. A lot of you maybe have had food with bay leaves in it and don't even recognize it. Why would you die from swallowing a bay leaf? Are they poisonous? No, they're not. You're not supposed to eat them, but why are you not supposed to eat them? Is it toxicity? Toxicity?
Nature's toothpick.
Nature's toothpick. Yes, they're nature's toothpick. And if you've had things cooked with bay leaves, and I had something yesterday. There was a bay leaf in it. Oh, I could have died. They don't soften when you swallow them. They stay hard and crispy, and sometimes they slice your intestine, and then it gets infected and bad things happen. So there's some very strange ways that you can go about dying. Now, another one that actually fascinates people, at least that fascinates some of us people, is another way is shark attacks. This was an article quite some years ago, but it's actually still a very popular article because it discusses the idea of a Poisson burst. And this has to do with the idea that every now and then, something that we think of rare and random events, we get a cluster of them. Okay, like several happen at the same time, several occurrences happen at the same time. And does that indicate non-randomness? Well, sometimes it indicates non-randomness. Sometimes it indicates simply the fact that if you get lots and lots of chances, occasionally you're going to get a fair number of occurrences at once. And so let's discuss, well, there's Simon Denis Poisson, though they left the accent off of the E there. So there's things about shark attacks.
Well, should we show the students an example of a Poisson burst?
Pardon?
Should we show them an example of a Poisson burst?
Could you give them an example of a
Yes,
Poisson
I
burst?
could, absolutely.
Okay.
Let's do it. I'm so excited to show you my show and tell item for today. Oh my goodness. Okay. My show and tell item for today is this little device, which we'll turn on. We'll put it on here on the dock camera to show everybody. And this is a Poisson burst device. Don't tell the TSA. Okay. What is this thing? Okay, let's turn it on. Can we read it? Okay, it's upside down. Let's see. My son made me add the color. Let's see, what color is the best?
You can zoom
Red,
in more.
no good.
Too.
Blue, no good. Okay, we're going with green. And let's zoom in a bit. And this thing has a little rate of 5 per second here. And its power is on, but it's set to mute right now. Let's turn it to loud and see what happens. And let's also move the microphone near it so you can hear it. What is this thing? Well, this thing is a little Poisson event creator. And every time it beeps, that's a Poisson event happening. And now if I set the rate a little bit lower, so I can change the rate on this thing, which is the fun thing, not to 0. But let's change it to some intermediate number, like 0.1. Oh, that's too low. That's too low to be fun. Let's do 0.5. So 0.5 per second is there should be, every 2 seconds there should be one. But every now and then we'll get a little, maybe a few in a row. Oh, did you hear that? There were like 3 in a row there. That is a Poisson burst. So this thing is going totally at random, according to this Poisson law that we learned. And so if you count the number of times it beeps in any time interval, it will always be a Poisson random variable. To get the rate parameter lambda, you do 0.5 per second times the number of seconds you waited. If I wait 5 seconds, that would be a Poisson with parameter lambda equals 2.5. But occasionally it'll just have a lot of beeps in a row just for no reason. And that's a Poisson burst. And then when a Poisson burst happens, you shouldn't go, oh no, something's wrong. Sometimes you just got unlucky. Sometimes you get unlucky the other way and it doesn't beep for a long time. Yeah.
Your beeper is not very loud.
It's not very loud. Yes. I had it louder and then my wife got annoyed that it was beeping a lot.
Can you increase the...
I don't know if you noticed, when it turns on into mute. This is an important property of this device. Otherwise, it will not work. Yeah, does anyone know what this thing is for? Like, why would such a device exist? Who created such a thing and why? The answer is I created this device to show you what a Poisson random variable is. I made it. It does this. I'll explain how it works maybe in a little bit as we go into our next topic. But this is a Poisson clock that I made just for you guys. Originally, it was always on green, and then my son came over and he's like, make it do different colors, Dad. So now it does different colors. Yeah, the fun thing I like about it, you can change the units here. I'm big into units. So let's make it go 1,800 times per hour. We can make it go much lower. Let's see, how low can I get over here? 360 per hour. So in this whole hour, it's only going to do 360. It's kind of quiet most of the time, and then we'll beep randomly. But this will have the Poisson bursts, and it kind of shows you what these Poisson events are like. We'll talk more about this later as we go to the next thing. Okay, there you go, a Poisson burst. That's my show and tell for today, and I hope you liked it. Okay, I have to turn it off now.
So an interjection before I go on to the next thing.
Oh, you're very zoomed in, by the way.
Oh, I'm very zoomed in. I am. Yeah, let's get back there. The Poisson distribution is scalable. And this is kind of, it's not something that's we would prove in the class. It's something you might prove in a math stat in your third year math stats class. But this is kind of interesting. You know, for example, if x is distributed Poisson with parameter lambda, then y equals ax is distributed Poisson with parameter a lambda.
Wait a second. I don't think that's true.
You don't think so?
I'll write this one down, and then write the one with the sums, and then we'll debate which one's true. Because I'm confused, which probably means the students are extra confused.
Okay. So what I'm saying, what I'm trying to say is that, for example, if x was the number of occurrences of whales per day, and we had an average of 1.2 whales per day, which is, that's the lambda equals 1.2. If we wanted to count the number of whales per week, well, a week is 7 days. And so the number of occurrences of whales per week would also be Poisson, where the lambda is 7 times 1.2. And if I wanted to do it per 10-day period, I could pick any kind of period of time. In a 10-day period, it's going to be 10 times 1.2, occurrence of 12. Going on a less than a day rate, well, the question is are they truly random throughout a 24-hour period? And that is something that is not necessarily well modeled by the Poisson. They may have their times of day that they surface and that kind of thing. But if something was truly Poisson throughout time, then you could scale that again, like the number of occurrences per hour, and again that would have over 24 hours it would have a lambda of 1.2 over 24. Now, Professor Nico's got something else in mind.
Yes. Okay, this is great. So I think the thing you wrote is essentially that the lambda is the rate of things happening, just like on this little guy, right?
Yeah.
The rate of things happening. Let's see if I can convince this to turn back on. And we'll put it back on to high, because that's fun. So if this is going at 5 per second, if you wait 10 seconds, that's going to be a lambda of 50. 5 per second times 10 seconds. The first thing you wrote, though, up here is
it's the AX.
It's not multiplying the number that happened in some time period. Okay, this thing is very annoying, actually. I am starting to agree with my wife. Let's mute. Okay. If you multiply the number of things that happen, then it's not waiting a full time period. For example, if a equals 2, 2 times x will always be an even number. You'll always have an even number over here. And the thing that you did sort of wrong is they have to be independent. So you need to have 2 independent sort of time periods, and then they add. But you can't multiply them like this because it sort of breaks the independence. But it is absolutely true that you need the rate times time
he
thing
is correct on that.
Yes. Okay. Very good. So let's cross this one out.
However, what I'm trying to get is that it's not the x that's being scaled
Yes.
by a, but rather the units.
That's right. That's
It
very
is
good.
the
Yeah.
units for x that are being
That's right.
scaled
Yes.
by a.
Yeah.
Yes, that is.
This is in pure probability class we call this infinitely divisible. Infinitely divisible, and there are basically only two distributions that are infinitely divisible. There's the Poisson and the normal, and you can prove that in some sense those are the only two. Although you can do funny mixtures of those two things, so it gets a little more complicated. But essentially, the Poisson and the normal are the two infinitely divisible distributions. That's a graduate probability thing. Let's not get too far into that. Okay.
Yes, so that's good. That's good. So back to what do I have to say about sharks?
Sharks.
You want to get onto something else too.
Well.
Okay.
We're getting into it.
Okay, we'll just see where we get to. Okay, that's all we know is where are we getting to. Okay. So just a comment on a good read on the shark attack article, but I'm going to go to, I want to leave that one, and I want to leave that one, just a second, blow it off of there. And so I got kind of fascinated in the shark attack business, and the Florida Museum maintains a shark attack database. And so if you're really into checking out shark attacks, which is a good thing to check out if you actually decide to swim in the ocean, they're very much focused on the U.S. shark attacks, but there's also data on worldwide shark attacks. A colleague I know did his PhD in Australia, and he told me he absolutely refused to go into the ocean in Australia. They get more shark attacks down there. You see news of people getting bad things happening down there. But anyhow, this is the database. If you're looking for something kind of interesting on rare and random events, or well, let's call them relatively rare events that can at least be approximately well modeled as rare and random events with i.e. Poisson distribution. There's some cases, and they make some comparisons between the number of lightning fatalities, for example, here, and number of shark bites, number of shark bite fatalities. Now, and this is summed over 1959 to 2010. So 459 lightning fatalities in Florida compared to 9 shark bite fatalities and 603 total injuries there. And so there's an interesting one in comparison. Hawaii has 6 shark bite fatalities, and Hawaii had no lightning fatalities. I wonder why they have no lightning fatalities.
Have you been to Hawaii? The weather's very nice.
Very nice. Probably no lightning.
There's no lightning.
There's no lightning. Yeah, so that can affect the chances of death due to lightning if you never encounter lightning. Anyhow, they have a whole bunch of various things that they compare the risk to various other things like tornadoes. And, you know, if you go in the ocean, what's the more likely thing to nail you?
Do they have one on here for heart disease? I bet you heart disease is worse than sharks.
Oh, I believe it's vastly worse than sharks. But so there's rip current fatalities. Again, they're, you know, I got a feeling they're kind of like apologists for sharks. They're picking out things that everything looks worse than dying from sharks. Whereas if they'd put bay leaves in there, they would find that fewer people die from bay leaves than shark attack.
I bet you more people die from being on their phone and running into light posts than sharks.
That could be.
They don't write those ones down though.
They got a few good ones: alligator attacks, bear attacks, dog attacks, home improvement equipment.
I need to see New York City biting injuries. This is
New York City
at the very bottom.
New York City.
This is great.
I've
What
looked
is
at
this?
that one. So they actually
number of biting. You notice they didn't say what species. Oh, human bites. Yes.
Dog bites human. Human bites human.
I'll tell you, as someone who's lived in New York for 6 years of my life, I would be most worried about the humans. The rats too, actually.
The rats.
The rats too.
The raccoons, they go down, well, there's a gerbil.
The monkey bites.
Yeah,
Watch out for the
monkey
monkeys
bites, snake
on
bites.
the streets of New York
bat
City.
bites, ferret bites.
Yeah, they say blue jay bites. Do you think they mean the baseball team? Like,
Yeah, that's kind of, it's surprising they got so few spider bites. That's kind of odd. Parakeet bites human. A possum bites human. Sea lion bites human. How the heck do you get bitten by a sea lion?
yeah, when it escapes out of the Bronx Zoo and you happen to be nearby, then
Right.
it can happen.
Anyhow, there's their total shark injuries in comparison. And then another one that's pretty interesting, I think, is the bicycle-related fatalities. We had a professor now retired who was an expert on risk assessment. I will mention that we have a third-year course on statistical methods in environmental risk assessment. So you kind of get into the analysis of risk-type data. And he was really quite a gatherer of data on risk factors, and one of the ones he maintained that was a very dangerous activity for the time spent on it. That's one of the things we always have to judge, is how long do you actually spend indulging in that kind of activity. But he maintained that one of the scarier things is bicycling. Now, many of you bicycle, right? Many bicycle. Anyhow, it kind of pointed out that you got to be careful when you bicycle.
But see, biking is a good one because it reduces your heart disease risk.
It reduces your
and
heart
then again,
disease.
the danger is the rate times the time, right? So if the rate is high, but you spend a reasonable amount of time biking,
Yeah.
then it won't be that high. Yeah, question over here. Yeah. Yeah, well, those are like truly rare events where we don't have, they're not in our distribution. The rate is so low. These are things these are like, again, they're rare enough that in any individual time you go biking, you're like, hey, pretty sure there's not going to be an accident. But they're common enough that over like hundreds of people in years and years, we do get a good sample. So the rate times the time, right? So you need a lot of trials and you need low probability on each one. Things like the Darwin Awards are so super rare that they're unlikely to happen even with everyone being weird all the time. That's why they're kind of exceptional. So these are kind of like rare, but not super duper rare events. Rare enough that in any individual trial they don't happen, but common enough that over many trials they are bound to happen. Yes.
Does anybody not know what Darwin Awards are? They're awards for people who have let natural selection remove them from the gene pool by getting killed in weird ways, such as going in and spraying in their bathroom because they saw a spider and they spray, and then they light a cigarette and it lights the aerosol and
so they got the
blows up
spider.
bathroom. They got the spider.
Yeah, great.
And took themselves out.
No
at the
spider
same
bites
time.
for me, please.
So Darwin Awards are, it's kind of morbid in one way, but it's also pretty interesting on some of the dumb things that people do to get themselves killed. Where are we? Okay, so I just want to leave. I'm going to leave that at that point there, and I'll pass it over to you.
Yes. Okay. This is a great chance. We've kind of said what we wanted to say about the Poisson. I think this is a really good chance to do a quick little recap of all the different named random variables we've learned so far. So we started with random variables that can be anything that is a random number, and you can come up with lots of weird and wacky ones. And there is no limit to the number of random variables in the universe, but there are some that are very common, and we've talked about a few of them. And it's worth, let's write all these down, because there's one that's missing, and maybe we can find the one that's missing that we haven't talked about yet. And I'm going to organize them in some funny ways. Let's write coin flips up here, because there were a few different random variables that were coming out of coin flips. Does anyone remember what the names of the random variables that go with coin flips are? What are some random variables you can make out of coin flips? You are sentenced to jail, and all you have is a coin flip, and you're like, I better make some random variables. What are you going to make?
Special probability distributions. Special probability distributions.
Yeah. Geometric. Fantabulous. So the geometric, that is one of them. The geometric has one parameter, and it is p, and that is the probability of the coin. So if you have a coin and the coin has probability p, is the probability to get a heads, So you have this special coin in your jail cell, and you're flipping it over and over again. The geometric is one of the random variables you can make, and it only depends on your coin. There's nothing else you have to decide. You just tell me what p is, and I know the geometric. And it's the number of coin flips until the first heads. The first heads. Okay?
So let's be careful on defining our geometric because
or-
we can be number of failures before you get your first head or the trial on which you get your first head.
Yes, very good. Let's write that down. Or, so this is the geometric I wrote is the 0 to infinity geometric. So this is the greater than or equal to 0 coin flip. That could be 0. Or there's the geometric greater than or equal to 1. That is, counting the first coin flip. I think we talked about this a lot when we had Evie in the class as our guest for the day. That you can either start at 1 or you can start at 0, and it's up to you. So if it's greater than or equal to 1, it's the number of flips, including, so maybe I won't say until, I'll say the number of flips up to and including the first heads. And then it always takes at least 1, the first heads. Okay, that would be a geometric greater than or equal to 1, or there's a geometric greater than or equal to 0. I think this notation is non-standard. People normally just write out what they mean. And then you have to know that it could be either one of these. But very good. So that's the geometric, and it only depends on p. There was one other one we made of coin flips. What's the other one? Yeah. The binomial, exactly. Yes, very good. And the binomial, it depends on p. So it depends on the coin flip. But you also have to decide something else, which is the number of times. The number of times you will do it. So n. And so this is the number of heads when you flip the coin n times. So you upfront decide, I'm going to do it exactly n times, and I'm just going to count the number of heads. And this is always between 0 and n. I'm going to say in this 0 to n. Let me write it the proper way. 0 or 1 or 2 or ... or n. So it could be any number between 0 and n. Whereas the geometric could have been any number greater than 1. So the geometric is, okay, depending on if you start at 1 or not, it's either 1 or 2 or 3 or, but it can go all the way up to infinity. Okay. This is very good because the binomial we have done a bunch with. We took 2 different limits of the binomial, and we got, starting from these humble coin flips, we got 2 different sort of exotic random variables that have these exotic formulas with e and stuff in them. And I'm going to write them down over here. There is the Poisson random variable that we were just talking about, and that has one parameter lambda. And there was the normal distribution, or the Gaussian distribution, or Gaussian, depending on how British you are. Gaussian, and that depended on mu and sigma squared. And that had 2 parameters. And both the Gaussian and the Poisson, they come from the binomial in different limits. And that is one way to get them. They also appear in other situations. But one way you can get them is to take various limits of the binomial. And in both limits, you let the n go to infinity. So the n gets larger and larger and larger. You do more and more coin flips, more and more coin flips. And then if you do more and more coin flips one way, you get the Poisson. If you do more and more coin flips the other way, you get the Gaussian. This is what we were talking about last class. And I had it in Desmos, the slider with the n getting larger and larger. The Gaussian is what happens if n goes to infinity and p is fixed. P is constant. Okay, and in that situation, you get this Gaussian random variable, and the mean and the variance will be related to the mean and the variance of the binomial. And this is the nice bell curve. And the weird thing about this is continuous. This is a continuous distribution. This is maybe one of the most important things to know. That's why we need our table. There's no nice formulas, so this is a continuous random variable. And the reason sort of it's continuous is because every individual probability over here as the number of coin flips gets bigger and bigger, the chance that you have exactly some number of coin flips is shrinking down to 0 when p is constant. And that's why you get this continuous thing. So that was how we sort of introduced the normal random variable and why it's important. The Poisson random variable we only did last class. And so this was the one, it has this, it's a discrete random variable that we've been talking about today. And it has this nice formula. So this one has boxes, and they look often they look like something like this. And it has a probability of being 0 or 1 or 2. And the reason that the individual probabilities don't go to 0, like in the continuous case for the Gaussian, is because as we make n go to infinity, as the number of trials gets bigger and bigger and bigger, the p-value is going to 0. The p-value is going to 0. And the p-value actually goes to 0 proportionally with this lambda. So p is lambda divided by n. So as the number of trials is getting larger and larger, the probability of every individual trial is going down to 0 in such a way that they balance, and the average number is exactly lambda. So the average number is always lambda. And that's another way to get the Poisson. And the Poisson and the Gaussian, they come up in all sorts of situations, not just from the coin flips, but this is like the mathematically easiest way to see where they come from. When we find aliens, the aliens will also know about the Gaussian and the Poisson because they come up in this like nice way from coin flips. Of course, they'll have different names. They didn't have Gauss, who was some guy, and Poisson, who was some guy who named these things. But they will know about the distributions, and they'll know about the number E, and so on, because they're sort of universal facts about nature. OK, I think these are all the ones we've learned about that have names. And what I'd like to argue is that there's something naturally missing here. There should be something that goes here that is kind of natural. And the reason I brought this for show and tell is because the thing that's missing can be heard on my little device. Let's turn this thing on. Let me turn the rate down a little bit so that we can, let's go to 0.5 per second. That was a good rate. And I'll put my microphone up to it in a second once we can see it. So the Poisson is counting the number of beeps that happen in any time interval. Again, by this formula, it's written right underneath it, rate times time, right? So the rate is set to 0.5 per second here. Let's go back, 0.5 per second. And then if you wait 30 seconds, then you should get 15 beeps on average. But the actual number of beeps will be a random variable. It'll be a Poisson with rate 15. The Poisson is like the binomial. It's counting the number of beeps. The number of beeps in any time interval is this Poisson. But there's another question you can ask about this guy. That's a very natural question to ask. And that is the thing that is missing on our nice diagram. There is a random variable that if you gave this to a child, they would ask, what is going on with this? What is the deal with this? And that is the random variable that's missing, and it will slot in very nicely on the board. What question would you ask about this little device? Beyond how many beeps did it do in a minute? What's a good question to ask? Yeah. How long between beeps? Right? It beeps, and it's going to beep again later. How long will it take? How long will it take? That is exactly the random variable that is missing. Let's turn this off before I go crazy. OK. And that fits in very nicely on our little diagram. Let me try to move this thing out of the way. Let's move this thing out of the way. Because we had the geometric, that was how many coin flips you needed. And then we did this limit where the coin flips became very rare. And the limit of the binomial was the Poisson. But what is the limit of the geometric? And that would exactly be the question of, let's do the same limit as before. So same limit. We're going to do the same limit where the number of coin flips goes to infinity. So same limit as Poisson. But now, instead of asking how many times did we get heads, we're going to ask how long did it take? Of course, if the things get rarer and rarer, the answer is going to be it took infinitely many coin flips. So you need to have some renormalization by time. But this is going to answer the question of how long, and you could think of it in seconds if you were thinking of the beeping device. How long, how many seconds between beeps? And that is a random variable. And even though we're in the same limit of the Poisson, where the number is going to infinity and the probability is going down to 0, the Poisson is counting the number of beeps. There's either 1 or 2 or 3 beeps. But if you ask how many seconds does it take between the beeps, that is another continuous random variable. So this will be our second example of a continuous random variable. And it has actually a very nice graph. So even though the Gaussian distribution is a beautiful bell curve that the aliens know about and comes up everywhere in nature, the graph is kind of, and it looks nice. You can't calculate anything with it. But this distribution has a beautiful graph that looks like this. It looks like this. Yeah, nice smooth. Okay, I didn't do it justice drawing it like this, but it's a nice smooth graph, and it starts at a certain value, and it is going down, it's decaying down like this. Has anyone seen a graph like this before? Yeah, I heard some people whisper it. This is like the whispers you hear of the PTSD of your high school algebra class. This is the exponential. Exponential. And so what is the name of this random variable? Exponential. This is the exponential random variable. Exponential random variable. And the exponential random variable, once again, I think the best way to think about it is if you have this little beeping guy with the Poisson, it is the time between beeps. Okay? Apparently it's a long time right now. You beeping? Oh, he doesn't want to beep. I don't know. We're getting unlucky. Okay, there we go. So the time between beeps, sometimes it's a long time, sometimes it's a short time. The time between beeps is this exponential random variable. We will learn more about them on Monday. In the meantime, there will be a homework assignment due next week with all the stuff we've learned so far about Poisson and Gaussian and so on, and that will be due next Friday. Okay, have a great weekend, and see everyone on Monday.